Я буду сегодня рассказывать сказки, и у меня будет более или менее два основных сюжета, которые, на первый взгляд, будут выглядеть очень по-разному, а в конце они встретятся и заживут счастливой жизнью. Okay, I'm supposed to speak English, I guess, right? Okay, sorry. So my talk is called the Interval Exchange Transformations with Flips, but I'm not sure that this title really reflects my plans for today, because apparently I would like to discuss two different plots, and then at some moment, as in all good movies, they are supposed to meet, some impressive story will happen among them, and then they will have joint future life forever and ever. So I will start from a very famous and quite old problem that Sergei Petrovich Novikov posed in 1984. 82, and 84 was the first paper about that already. So it was in 1982. He was interested in physics of metals, and in particular he was studying semi-classical motion of electron in crystal lattice and the presence of magnetic field. And so he built some kind of rather elementary mathematical model for the physical model that was introduced by Russian School of Theoretical Physics much earlier in the 60s. So I will present already a mathematical model and then say a few words about physics, but will not be very precise. So imagine that you have a three-dimensional torus in R3, and you have some surface that is embedded in this three-dimensional torus, and it's a smooth function, level surface. You have some function, and this surface is its level surface, and it lives in three-dimensional torus. And since, sorry, I will want hat to be here. I will put hat on this recover. This recover of n. So this will be a three-periodic surface that lives in R3. And I will need one more construction. It's just a natural projection from R3 to T3 that appears to be a factor R3 over some lattice. So it depends what do you prefer. If you want, you can think about it in the following terms, that you live in R3 and you have a three-periodic surface. Three-periodic just means that it's invariant under translations on vectors from some integer lattice. And you have pi as a projection from R3 to T3, which is the factor of your R3 over this lattice. And then you have a function, which is the image of your original three-periodic surface under this projection, and it will be a function of some it will be a level surface of some smooth function. So what we would like to consider, we fix some vector, and we consider all planes orthogonal to this vector. So we will have a family of surfaces that are parallel to each other. And we are interested in a typical behavior of the intersection of our surfaces with this family of parallel planes. So if you prefer a physical interpretation, you can think here about the Fermi surface of some metal and vector which will be responsible for the magnetic field. And so this intersection will provide you trajectories of the electron when it moves in your crystal lattice. Otherwise, if you are not a physicist and you prefer the more mathematical interpretation, you are used to live in a world of Riemann surfaces and some foliations on them, you can ignore this m hat and consider already m as it is. And so instead of plane sections, you can think about a one form defined on T3 that will have the components of this vector as coefficients. The coefficients will be constant. And so this one form will indicate a one form on your surface. And this one form and the surface is a typical pair that defines a measured foliation on a surface. So otherwise, you can think about these two guys, that they provide you a measured foliation on a surface. And so if you have a measured foliation, there is a natural question which is pretty connected with this one. What can one say about the behavior of leaves of this foliation? Novikov posed his problem in '82, and immediately after the first result by Anton Zorich appeared, and later Ivan Dynnikov, who also at that time was a PhD student of Sergei Petrovich, clarified Anton's results and extended them. And so the final picture is the following. Let me consider the most generic case when we think that all the components of our vector H are rationally incommensurable. In such a case, we have the following classification of the trajectories in this interpretation. The first option is so-called trivial case. Triviality means that everybody is closed. All the components are just compact, bounded, and so on. That's what you have if, for example, imagine that as an example of your surface, you have some kind of a fat cross. So you take a cube as a fundamental domain of your lattice, and you consider a fat cross inside of this cube. So this is a cube. This is a guy that I call fat cross because I just have to take centers of the faces and consider the construction of 3 small sticks, and then I replace my sticks with cylinders and try to make a surface that will be as smooth as possible from them. Something like that. Here is the nose, and here will be the last part. And so if you will consider the section of such a surface by a plane which is parallel to the face of your cube, you will have as a section just some circle, and this corresponds to the trivial case if you start on the, you start somewhere here. So another option which is much more popular and which is the most standard one somehow is called integrable. That means that the following happened to your surface here. You take a surface and a foliation on it, and your surface is cut into components of genus 1. So you have tori, and you have a decomposition of your surface into the collection of some number of tori. And on each tori, your foliation is just a rational winding, or maybe rational winding, but then you have also some trivial components. But anyway, what happens is that by saddle connections, your foliation is totally decomposed into the tori with foliation on it. And if you prefer the interpretation in terms of 3 periodic surface and its section, that means that your trajectory looks like a perturbed line that lives in a strip of a finite bound, and moreover, it lives in a very correct way. It does not go back, it does not self-intersect, it just lives inside very accurately and behaves almost as a real line. In this case, what happens to you is that you have a kind of a very strong asymptotic direction. So you cannot really say that your trajectory is a line, but it follows the line quite closely and quite accurately. And the last option, which is the most interesting and which was not obvious to exist at all, is so-called chaotic case. Chaotic case corresponds to the situation when your foliation has some your surface has some components of genus at least 3, such that the foliation is minimal on it. By minimality, I mean that your leaves are everywhere dense. So you are supposed to have a minimal component of quite a high genus. What does it mean from the point of view of geometry of the corresponding trajectory? It's much less obvious with respect to integrable case. However, you can understand that you basically do not have a strong asymptotic direction. Your curve lives somehow on the plane. Imagine something like a dragon curve. In reality, what we are able to show in some particular examples is that still we will have some kind of leading direction. But still, from the point of view of level of asymptoticity, it's not comparable to integrable case. So here we are missing asymptotic direction in a strict sense. So this situation is the hardest one to find out, and indeed the first example was built in the context of Novikov's problem quite late. In 1997, Dynnikov constructed it. It was the last theorem of his PhD thesis. But in reality, people used to know some examples of such a behavior much earlier. They just did not realize that it's an example of chaotic behavior in Novikov's problem. Because I will tell more details in a few minutes, but apparently a very famous object, which is called Arnoux-Yukos diffeomorphism, that was constructed exactly the same year as Novikov described his problem, but in French. And this example serves very well as an example of chaotic measured foliation on a surface. Just people did not know about the work of each other, so somehow the field's medalists did not understand that they are working on a very similar stuff. So Dynnikov did much more than just this. He did not stop on a classification. He also proved that integrable case is somehow the most popular one. More precisely, his theorem states the following thing. It's from the same paper of 1997, that if you consider pairs of M and H, so you can think about, at the first glance, it looks like you live in a space of infinite dimension, but it's not true, because in reality, you don't need to know the whole surface. It's enough for you to understand what's going on with the singular points of your foliation. It's enough to know where saddles are located and what are their relationships with each other. So if you restrict yourself to the space of these pairs, all chaotic regions that you can find will live in a set of codimension 1. In sense, I will explain what I mean more formally. If you look at this interpretation, that means that you consider your function as a level function of some, your surface as a level surface of some function. And what happens is that normally when you vary the values of this function, you will never get a chaotic region except one particular value. So it only happens if you fix some function. It only may happen. It does not happen always, but it only may happen, this chaoticity. It may only happen for a one particular value. If you prefer to think about foliations, then you can just decide that it happens only for a codimension 1 set of the parameters. And then in this codimension 1 set, let me denote it by R, it forms, chaotic regions are still not very popular, even inside of this particular set. They form a nowhere dense set. So once you understand that some set is nowhere dense, it's almost automatic in dynamical systems to pose a question. Either it has a measure 0 or not, and then even to ask yourself, what about the Hausdorff dimension? So typically, these kind of results are much easier than the results about the measure 0 statement. Because this you understand. You can just use this kind of technique with G delta sets, and there you need to proceed already to something that you're supposed to measure. So there was a very natural question that has a formal name of a Novikov's conjecture. Novikov's conjecture. It was formulated by Novikov in his joint work with Andrei Maltsev in 2003, that apparently chaotic regions form a zero measure set in this particular set R that we fixed in Dynnikov's theorem. And moreover, we can even estimate a Hausdorff dimension, somehow proving that it's a real fractal, that its Hausdorff dimension is smaller than the dimension of the set -1. But I will not discuss much the Hausdorff dimension part today, despite of the fact that I worked on it for some time, but I want to concentrate just on a measure zero statement. Measure zero statement for chaotic regions. So,
Sasha, I'm sorry, can I ask a question about
yeah.
Lee and Jim? So are you saying that these three cases exhaust all the possible situations, or is it just three nice?
No. They really cover everything, because indeed I did not discuss what happens when genus is equal to 2, and it's another theorem by Dynnikov from the same PhD thesis where he proved all other statements I mentioned. That here he explains that if you have a surface of genus 2, it will necessarily decompose always into the tori with some foliation on it, so it will be always integrable case. So everything interesting starts only from G equal or smaller or greater than 3, and then in this case you always may have chaotic regions, otherwise you will be decomposed into tori, and then you are in the integrable case. Nothing else may happen despite this. If you remove this restriction, you may have something else. There was a work by Sergei Tsarev that was never published with some examples, but today I don't want to go so much into the details. I think we can restrict ourselves to the most generic situation when they're really rational and incommensurable. So this conjecture in this level of generality is still open. What we are able to do, the conjecture is proved for a very particular situation when you consider a special surface, the surface of genus 3 with a lot of symmetries in it, quite similar to the example I provided here. From the topological point of view, what you have, so example in which it's proved, it corresponds to the case when G is equal to 3 and we have two double saddles as the singular points of our foliation. It has a lot of symmetries, and it's a very particular case. Otherwise, what is the most meaningful from the physical point of view is Novikov's conjecture in a context when our surface M is somehow centrally symmetric. Because it's a Fermi surface of a metal, as I told you, and the metals are supposed to have quite symmetrical Fermi surfaces. They have lattices and so on, they are very symmetric, they like to have many symmetries. So the most meaningful question that we can pose here is either Novikov conjecture holds or not. In case of symmetric surface M, say we restrict ourselves to the case of genus equal to 3, because the higher genus are more complicated to analyze. And what I'm going to discuss today and the rest of my talk mainly, there are two aspects. One is why it's kind of a hard problem, and the second aspect is why do we think now that we have a solution for it. So the first impression that people who ever measured foliations usually have at this moment is that, well, it should not be very complicated, because somehow measured foliations were very widely studied in the dynamical systems starting from 60s. Plenty of very brilliant mathematicians contributed, and they developed a technique that I will briefly outline in a few seconds, which is related to interval exchange transformations. So their first impression every time I try to explain the problem to some people who already saw measured foliations is that, okay, but that should be trivial. But I will first explain you why they think so, and then explain why it's not true. So, measured foliations on a surface, what we have usually, imagine that you have a surface, a smooth one, and you have some real closed one form with zeros. And what does it mean that we have some measured foliation defined by this one form? It just means that we have a foliation such that the leaves are everywhere tangent to the kernel of this one form. So it's a foliation such that the leaves are tangent to kernel of our one form. And then why it's called measured? Because there is a natural measure that we can associate with it. And this measure is invariant under the holonomy map. And the measure comes from the fact that we can integrate our one form along the leaves of the foliation. So what do people understand about these guys? I think they started to study them on the surface. I mean, foliation will be, the foliation is measured in the sense that you can put a measure on the leaves. And you can measure the distance along the leaves by integrating this one form along these leaves that you have. And the distance will be preserved in the sense that it's invariant under the holonomy map that you have here. So apparently, what is the most standard instrument to study this kind of people? It is the same instrument that people introduced when they were looking on the billiards in rational polygons. And you have to look at the first return map on some smartly chosen transversal. So you take a transversal to your foliation, and then Poincaré recurrence theorem guarantees you that you are supposed to be back almost always to this transversal. And what may happen to you on your road is the following. Typically, 2 points that were very close to each other, if they departed together, they will be back together, unless they met zero of your form somewhere on their road. And zeros of the form, what is their role for the foliation? They correspond to the singularities of the foliation, and your singularities are typically saddles. So what could happen is that you have such kind of picture and 2 points that were very close. Then they had very different trajectories after because they were separated by a separatrix of the corresponding set. So as a first return map, you get the following object, which is called interval exchange transformation, and that has very, very simple definition. So you take an interval of a real axis, you divide it into several parts, and then you mix these parts and consider orientation preserving isometries on each part. So these points, they all together go to this part, these points all together go to this part, these points all together go to this part, and the ends of your subintervals correspond exactly to these moments when you are supposed to be separated by a separatrix on your way to the saddle, right? So close points, they travel together when you look at your foliation, unless they met at some point, the saddle, and then it will separate them, and their return time will change. So you mark by the same sign those who return together. And if you have a measured foliation on a surface, you always can build interval exchange transformation. And the question about the behavior of leaves of your foliation can be replaced about the question of orbits of interval exchange transformation. What does it mean, orbit? It just means that you have a collection of measured preserving isometries. Altogether, they provide you a map on the interval of real axis to itself. And so you can ask, where did your point go under the action of this map? And you can consider, for instance, either it's closed or everywhere dense, or what it is doing, right? So you can replace the question about typical behavior of leaves here by the question about behavior of orbits for interval exchange transformation. And apparently, the opposite direction also works very well. If you have already interval exchange transformation, you always can build a surface and define a foliation on it in a way that this will be the first return map to the transversal and so on. So once you have a measured foliation, you can find an interval exchange transformation. Once you have an interval exchange transformation, you can always define a measured foliation. There is kind of a duality. Then there is a natural question, is it true that if you choose different transversal, you will always have the same interval exchange transformation? Of course, it's not true, but it's also true that you can easily understand the relation between your original interval exchange transformation and the new one. I'm not going to make a mini course on basics of IETs and Teichmüller dynamics in general, because I think that nobody is motivated enough to sit here for several hours. So I will just outline the main results in order to explain you why Novikov's problem on the first glance fits in this context, and on the second one does not. So I will need two things. First, I will need to make a list of results that people already proved about IETs. And second, I will need to explain what was their main tool to prove these results. So what are the questions we can pose? In a similar way as here we wanted to understand either our leaves are everywhere dense or they have closed orbits and this kind of stuff. Here we can also ask ourselves, is it true that ET is minimal? Not. Then
What does minimal?
Minimal means that all orbits are everywhere dense. Or if we have closed orbits, and then you can increase the degree of kind of a good behavior of your dynamical system from the point of view of ergodic theory. So you can ask, how many invariant measures does it have? Of course, the first one is a Lebesgue measure. It's invariant, just by definition. But if you have anybody else, so is it uniquely ergodic? Is it the only invariant measure that we have or not? And then I will not even write it up, but you can believe me that you can increase the degree one more time and start to ask yourself about mixing properties of this map. But we will preserve it for the seminar of ergodic theory, and I skip this part about weakly mixing, strongly mixing, and so on and so forth. In any case, what we can do, we can build some kind of ergodic theory for this kind of maps and apply it later to the original question about ergodic properties of the measured foliation on the surface.
The answer to your question depends on the intervals and on how you mix them.
Sorry?
So there are several questions. Your system depends on your intervals.
Yes, you need the length and the order. Say you have a permutation that tells you in which order they appear on the top and bottom level, and you need the length.
And the answer to your questions, they depend on the data.
Yeah, of course. But so somehow what we would like to understand, there are two different questions. One is, if we have a particular EAT, is it minimal or not? Is it uniquely ergodic or not? And the other question is like, is it true that almost all of them satisfy one of these conditions? Like, can we say something about the majority of interval exchange transformation? I will provide you the answer and then explain quite inaccurately the instrument that you can use to get it. So the first question is the first result is the following. First, let me make one more remark. Imagine that we have some interval exchange transformation, and let us look at the permutation pi. The permutation pi is responsible for the combinatorics, for the order of intervals in which they appear on the top and bottom level. If it happened that the permutation pi can be just splitted into two different parts, something like that. These two guys, they only mix with each other, and these two have their own life. In such a case, of course, the question about minimality is quite retarded, because anyway we will not have everywhere dense orbits, because all the dynamics for these two people are concentrated on their half, and these two guys, they live in a communal apartment and never exit from their rooms. They live separately. So you will not have minimality for sure. This kind of situation is called reducibility. So we will call the permutation reducible, not like in algebra. It's a much simpler notion here. It's just reducible if it splits into two independent parts. Let us forbid this situation and agree that we will always live in an irreducible world. If we agree that pi is irreducible, then apparently typical interval exchange transformation is minimal. Kin, 75. So almost all these are minimal. He even provided a much more precise statement. He gave a condition which is sufficient for minimality. More precisely, he explained as the following. Let us assume that these critical points, the ends of the subintervals, they never meet in the same orbit. It just happens that they never appear in the orbit of each other. Then it's enough to guarantee that interval exchange transformation is minimal. We need to remember this condition. I have to acknowledge immediately that it's a sufficient condition, but it's not necessary condition. I mean, it may happen that Kin's condition is violated, but interval exchange transformation is still minimal. And apparently, despite of the fact that he understood it already in 1975, and if Sasha Bufetov would be here, he would tell me that oscillations was even earlier, and we would start to argue about it. But so it's many years ago somehow. The question, if we can say something about minimality of family of interval exchange transformation that does not satisfy Kin's condition, is still open. So if you give me some family with some rational restrictions between the lengths of the subintervals and ask me either it's true or not that majority are minimal, it can be very complicated question. And in such a generality, it's an open question still. So, moreover, Kin formulated a conjecture in the same paper that was proved independently by Vilvich and Hoemezur in 1982, two papers in the same issue of Annals, that almost all IETs are uniquely ergodic. I'm not going to discuss at all what does it mean almost all here, because the condition is not so nice looking as in case of Kin, and also since I restricted my study of Novikov's problem just to minimality, I don't care that much about unique ergodicity today. I just want to show you how much people understood already about this kind of persons. And so I need to say just a couple of words about interval exchange transformations in this case. How did they treat them? How were they able to prove something like Kin's statement? And what is the reason why it works? Apparently, you can do the following thing. Having interval exchange transformation, you can define another one that will live on a smaller support interval, but will have the same behavior of orbits. So technically, we have some kind of induction process that looks more or less like a Euclid algorithm for numbers that allows us to start from some interval exchange transformation and to construct another one which is equivalent in the sense of orbit behavior, but lives in a smaller interval. And if we are allowed to do this, to apply this process forever and ever, then somehow we are sure that we are in a minimal situation. Because starting from every point, we can go to the sufficiently small neighborhood of it, right? Applying our procedure. And this procedure is just a first return map to some subinterval. You look at the longest possible subinterval that has as ends your singular points, which is different from the original one, and you consider the first return map. I'm not going to discuss all the details, but you can check that apparently if you had irreducible permutation, you will have another interval exchange transformation as an induced map. And if you started from irreducible permutation, you will go again to the irreducible one. And the connection between the lengths of the old and new interval exchange transformations will be given by something similar to Euclid algorithm, so it will be just difference between two. I don't want to eat much time from you now to convince you with it, but it's rather simple thing. And this procedure is called Rose induction. So if you do not have any rational relationships between your lengths of the intervals, and so Keen's condition is satisfied, then you can last your Rose induction for as long as you want, and so it will allow you to build an interval exchange transformation on a very, very tiny interval, and so you are sure that you had minimality because you can enter every small neighborhood. Otherwise, you don't know how to proceed, so you don't know what to say in case if Rose induction is not applicable. So when I explain to some quite brilliant people Novikov's problem, and if they did not hear about it from Anton before, they looked at it and they told me, okay, but it's a measured foliation on a surface. You're just supposed to write up your interval exchange transformation, apply your Rose induction, and get the result. Why do you come to us to ask? However, it's not so complicated to understand that, unfortunately, Keen doesn't know anything about Novikov's problem. His condition is simply not satisfied in case of Novikov's context. Why? Because we live in a three-dimensional torus. So if you prefer a topological language, you can understand that when you take your one form and integrate it over the basis of in your homologies, instead of 6 independent intervals in case of genus 3, as you are supposed to have when you work with a generic interval exchange transformation, you will have just 3 of them. Literally, it means that if you try to write up interval exchange transformation that corresponds to Novikov's situation, you can do it. It's not forbidden. You can do that. But you will have an interval exchange transformation with plenty of rational relationships between the lengths of your subintervals. For example, in this baby example case that we considered, in which Novikov's conjecture is proved, the family that you're gonna have is a famous family that appeared more or less the same years in late 80s, I think, in interval exchange transformation and symbolic dynamics. It's called the Arnoux-Razi interval exchange transformations, and you will have 7 intervals, but just 3 of their lengths will be independent. All other 4 can be expressed in terms of these 3 with the rational coefficients, with integer coefficients. So that means that unfortunately all these cool theories that strong people developed for us in context of Novikov's problem is just good for nothing. So we need something else. We are not allowed to apply Rose induction as it is. Now let me leave for a moment Novikov and his questions and concentrate on a part which is kind of more ergodic and more abstract. Namely, I will introduce people that are in the title of my talk, interval exchange transformations with flips. I'm supposed to explain you who they are, what do they have in common with these people, and why they are different. And at the very end, you will get a kind of a surprise because we will recollect Novikov from the past and connect these 2 stories. So, okay, interval exchange transformations, as I told you, they can be seen as a first return map for the measured foliations on the surfaces. But it's not the only reason why people like them. In particular, those who were working like Katok with billiards in rational polygons, rational just means that all the angles are rational numbers multiplied by pi. So they also found the same guys as the first return maps on some transversals for the billiard flow there. And they started to pose the same questions, but they did not care about homologies and one forms. They wanted to understand what's going on with their billiard flow. And then, okay, the way they treated them was very similar, but people from this world, they generalized this notion. And they removed the restrictions that we need to preserve the orientation. Transformations with flips. So what happens generally is the following. As in case of ET, you still have an interval, you divide it into subintervals, and you mix them. Very similar. But however, now I do not promise you that I do not touch the orientation. So what I can do is, for instance, flip some of these intervals. I will reverse the orientation in my identifications. Very natural question is, why do you want to do so? Like, if we have any motivations that would be natural. People who introduced it, they were thinking about a very particular class of billiards, which is called billiard in rational polygons with flips. But to be honest, I never understood why did they like them. And for me, it's much more natural to think the following, that you take a foliation. But here, I did not stress it. It was my mistake not to do it. But in the context we discussed before, the surface was oriented and the foliation was oriented. And two orientation agreed with each other. However, sometimes you may have a non-orientable surface and still define a foliation on it. And then interval exchange transformations with flips will appear in this context when your foliation is oriented but not co-oriented, in the sense that its orientation does not agree somehow with the orientation of your surface. So it has some geometric motivation, even if it appeared with totally non-geometric reasons. We have this map. We are still interested in the same type of questions.
Sasha, I'm sorry.
Yes.
You say that you flip everywhere?
No, right now, it's a good question, but right now I just allow some flips. I don't say that all the intervals are supposed to be flipped. At least one pair has to be flipped. So, I mean, you take some subinterval, which is an interval of continuity of your map, and there you have a map with that is orientation inverse, that inverses the orientation. But on some intervals, for instance, like on my picture, like this one can be not flipped, but if at least one person is flipped, I will already call it interval exchange transformation with flips. So it was introduced by Arnaldo Nogueira 30 years ago, and Arnaldo immediately understood that despite of the fact that they look very similar to interval exchange transformations, these guys are much worse in their behavior. They like to have periodic points. So what Arnaldo proved is that typical interval exchange transformation with flip has periodic points. It is not minimum. And you can, even if there is only one. So I will explain you why it's true and what's so much different with respect to a normal interval exchange. Standardly, people, again, who got some experience with the classical interval exchange, they would do the following. They would try to define the same type of induction and try to apply it and see if they can do it forever. But what is wrong in such a case is that it's not true anymore that if you started from irreducible permutation and you apply some type of induction, you get irreducible permutation again. In this case, you easily can have reducibility. You started from one permutation and you finish in a permutation which is reducible, and so there is no minimality anymore. And how did he prove his theorem? He observed the following thing, that if your flipped interval, if you have at least one pair of flipped intervals, and this flipped interval is long enough, it's longer than 1/2 of this interval, then you definitely have a periodic point. And then he showed that on each stage of application of his induction, he will have some positive measure of parameters that provide him this kind of interval exchange transformation with a long flipped interval. And then it results in effect that step by step, these guys with periodic points will eat everybody. So apparently they have very, very different behavior of their dynamics is totally different. Then his results was refined by Serge Trubetskoy and myself. when we estimated the Hausdorff dimension of minimal ET with flips, and we showed that it's strictly less than n minus 1, where n is a number of intervals, but greater or equal than n minus 2. So it's very small set in the sense that it's a real fractal, but it's not that small still. If you have a lot of intervals, it's relatively big. So you can ask me if anything is known about these minimal interval change transformations with flips. For instance, if we restrict ourselves only to a minimal guys, can we prove something which would be similar to Witch and Mazur about unique ergodicity? But apparently, it's a hard question, because this induction works in a very unknown way to them, and so the graph you kind of, the combinatorics you have is very complicated. And something like that, only in case of 4 intervals, it's a plot of thesis of my student Paulina Baron, who will graduate in May. So kind of, it's complicated to treat them, and basically there are no abstract results about them. For the case when we have more than 4 intervals, everything starts to be very hard to understand. Okay, good. So now we are ready to define a particular class of them. I don't want to work with them in such an abstract way anymore. I will define a very particular class of them. It's a pity that Jenny had to exit, because it's exactly a class he asked me about unwillingly when everybody is flipped. And I will explain you something about this class and cite some results, and then close my ring with Novikov's problem. So, fully flipped. Actually, up to now, I always lived at the interval, but I don't want to do it anymore. I want to move to the circle. So these guys, they will live at the circle, so instead of interval exchange, I will write circle exchange transformation. Nothing changed, just 0 and 1 is the same point for me starting from now. And what will happen is the following. Again, you see, I have some results, not me necessarily, but people proved something about the whole class of interval exchange transformations with flips, and even introduced some kind of induction, despite the fact that it's not so nice as the original was induction for the standard interval exchange transformations. But now I want, for some crazy reasons, to consider a subclass of them, a very particular situation when all intervals are flipped. So imagine that we have the following, and we are now at the circle, so I may do things like that. Some intervals will be divided into 2 because we are on the same. So what does it mean that I have such a map? It means that I will do the following things. I will flip all of the intervals, and since I will also rotate my circle. Maybe my picture is not, it's not the best one. I will do this. So I will have now one more parameter. I have my lambdas, which are responsible for the length of the interval. I know their order now because I live on the circle, and on the circle I'm not allowed to mix them as I want. I will preserve their cyclic order. But I will add one more parameter, which will be responsible for the translation on which we slide when we do our procedure. And we agree that all intervals are flipped. So again, the most natural question is, why do you care about it? And the motivation originally came from so-called tiling billiards. Tiling billiards. I need to mention a few people in this context: Pat Cooper, Diana Davis. Diana has a few publications about it with her undergraduate students. Let me avoid to cite all of these people because there are quite numerous amount of authors in each paper. And Diana says that the first person who told her about this stuff was Sergei Tabachenko. So they were working with a very particular type of billiard. What does it mean, tiling billiards? We are not going again to discuss it much, but since I announced the words, I have to explain a little bit. It means the following. You take tiling, for example, triangles, you just take the standard equilateral tiling like that, and then you consider a billiard. So you take the trajectory, and every time you touch the side, you continue in another side, but you respect the fact that your two angles are supposed to be equal, and so on. And you are interested in the behavior of orbits of such a billiards and some geometry associated to it. And it was an observation that was made by Akiyama that interval exchange transformations with flips, fully flipped interval exchange transformation on a circle are exactly responsible for the dynamics of these tiling billiards. He did it for the triangles, but you can also generalize it for the squares as well, his approach. We are not going to discuss the details of these constructions. It's quite a beautiful, pure geometry in the school sense, because you need to consider some circles, centers of these circles, triangles that live inside of the circles, and so on and so forth. It's very simple. Pictures in their talks are usually a great pleasure because you see very beautiful pictures, but since I was lazy and didn't make the slides, we skip it. So now we are going to ask ourselves, okay, we consider such a dynamical system. What can we say typically about minimality of fully flipped interval exchange transformations? And there is a result by Pascal Hubert and Olga Romaskevich-Paris. That in case of 3 and 4, minimality happens only if tau is equal to 1/2. So this is a Pascal Hubert. Their proof is quite complicated, I have to say, especially for the case of n equal to 4. It's a computer-assisted proof, and it's quite painful to follow it, and they published it in Experimental Mathematics exactly because it relies on a computer program. However, in this paper, they noticed that actually the set of parameters for which in case of 3 intervals, if tau is equal to 1/2, so we will have just 3 intervals that are responsible for the length of the corresponding fully flipped interval exchange transformations. So the set of parameters for which indeed we have minimality is a very, very famous set, which is called the rosy gasket, that appeared already in Novikov's problem in these examples that I mentioned, in the only situation when we are able to prove accurately Novikov's conjecture. So they started to be suspicious. It looks like the same set, which is rather specific fractal, appears in 2 very different problems. Is it true that there is some relation between these 2 things? Asked me Pascal Hubert in Vienna in July. And I came home, and I met Ivan Dynnikov, and I posed him the same question, and we played a little bit, and we realized that this theorem is just a corollary of Dynnikov's theorem that I wrote some minutes ago. The statement that chaotic regions in Novikov's problem always live only in a set of codimension 1. If you remember, I told you, how does this set appear? That we consider our surface as a level surface for some smooth function, and for most part of values we will never have a chaotic region, But for one particular value, they can appear. And this particular value exactly corresponds to this value of the parameter tau. I will not prove it to you right now, but I will explain you what exactly we did. So in case of n equal to 3, it's more explicit. In case of n equal to 4, it's less explicit, but still, we have a model. I will make it more or less understandable for you. Not very accurate, but imagine that you take a rectangle and you make a few cuts in it, exactly 3. I make a picture for n equal to 3 because it's simpler, and you do it. I'm very inaccurate, too inaccurate, I think. We need to fix the length and the cyclic order. Maybe my picture is not precise enough in the sense of cyclic order, but I explain you just general idea. So imagine you take a rectangle and you make 3 pairs of holes. You make holes accurately from the sides, and you do it in a way that these holes are small rectangles. Their heights are almost 0, and their widths are equal to the values that define the values of the parameters, for instance, here. So here there is length A, and here is also A, here is B, and here is also B, here is C, and here is also C. Now, what you do, you start to glue. You associate the opposite sides of your cut. So the upper side is associated with the one which is down, and the upper side here is associated with the one which is down here. So you do something like that, and you continue. And then at the end, you associate these 2 big sizes too, and these 2 with each other. It's very easy to understand that in such a case, you will have a surface of genus 3. Because you started with a kind of a tori, you have all these holes, and since these 2 guys are glued, you will have a few holes in your tori, so it will be exactly a surface of genus 3. And if you define vertical foliation on this rectangle, just like that, you will have a surface with a foliation on it, with a measured foliation on it, moreover. And what happens in reality is the following, that you may find a transversal. It's not obvious at all, but you can do that. You can find a transversal here that will give you some permutation, and then your surface that you constructed in this way, it is very symmetric surface. So there is some involution on this surface. And then you can factorize on this involution. And in such a case, as a first return map, you will have not an interval exchange transformation anymore, but a fully flipped CAT. And it will be exactly the same fully flipped CAT as we defined here. So the behavior of orbits of the foliation we defined here totally coincides with behavior of orbits of the object we defined here. And we have just explicit connection between these 2 things. You can draw a picture and provide it. And it works in a similar way. In case of n equal to 4, it will be the same. Just you still have 3 holes. Just this one pair will not be glued to the side, but will be somewhere in the middle in a symmetric way. And so in case of n equal to 4, for example, what you have, you will have the following interval exchange transformation, like that. And so it will kind of mix 2 components, and then you have an involution that switches the guys that are waved with the guys that are not waved, and so you finish in a fully flipped circle exchange transformation with n equal to 4. So this person represents an example for Novikov's problem. You have a surface of genus 3, and you have a foliation on it, and you can check that it fits in all the requirements for Novikov's problem. And then it means that minimality of this person implies the fact that the corresponding foliation in Novikov's problem should be chaotic. And so this theorem is nothing else but a direct corollary of what Dynnikov did. We found some other more simple proofs that exploitates this model, but I don't want to discuss the technical details. I just want you to understand that this fact that looked totally different, and indeed it was proved very differently, it just follows from something that was known already much before. And then the last thing I wanted to mention is the following fact. Now I explained you how did kind of Novikov's problem theory served to a pure dynamical systems and geometry. We can take Dynnikov's theorem and apply it here and get for free a proof for this result. Now I will explain you the opposite direction. So we start with a fully flipped CETs on 4 intervals, and we understood that it is in a one-to-one correspondence with chaotic minimal fully flipped CETs are in one-to-one correspondence with the chaotic regions exactly in case of genus 3 and symmetric surface. So now we want to prove the Novikov's conjecture for it. We want to understand, is it true that these minimal guys occupy a set of zero measure for, in a sense of parameters lambda I for fully flipped CETs. And apparently it's true. And the result, it's a work in progress with Ivan Dynnikov, Pascal Hubert, and Paul Mercat. That Novikov's conjecture is true for G equal to 3 and symmetric surface. So we use this duality to switch the question to the question about fully flipped circle exchange transformations, and now we have to ask ourselves, what can we do with them? The main difficulty comes from the following fact, that if you live on the circle, first, if you live on the circle, it's much harder to apply any induction, because induction does something on the interval and typically not on the circle. So in order to go back to a standard context of inductions, we want to open our circle to make the circle the interval again. And we want to work on this interval, but in such a case we will have not 4 but 5 different lengths with some rational relation between them. 4 will be independent, the 5th will depend on this other. Then the next difficulty is to find an induction such that, on the one hand, it will look nice from an ergodic point of view. In particular, we prefer if we are able to express all coordinates in terms of the new one with just positive coefficients or non-negative ones. It's a standard technique in ergodic theory. But we also want them to be respective in a sense of these rational relationships that we have. So if you start in a kind of too direct way, you would fail. That's what happened to me some years ago. I understood similar things, but I failed. But what Paul Mercat suggested, he wrote a computer program that found some nice induction in this case. And then Pascal Hubert and myself understood, with a lot of help of Paul, what does it mean geometrically? Why this induction indeed has some geometrical sense, why you should take exactly these inductions that Paul proposed just from experiment. But what happened, how this theorem is proved, it contains 2 parts. One part is what I tried to explain here, that there is one-to-one correspondence between chaotic regions and minimal fully flipped interval exchange transformations. And then there is a second, more technical part to construct some induction for fully flipped interval exchange transformations, and to prove for them that minimal occupy a space of zero measure set. So this is a work in progress. It's not totally written. And in any case, just to finish, I was given a question about Novikov's conjecture for symmetric surfaces as a plot of my master thesis. It was 11 years ago. And it seems that if we will not find any mistake, like in 1 year, I will get my master thesis finally. So thank you very much for your attention. I think we should stop here. With higher genus, it's much more complicated because you have more parameters and all this business with inductions goes out of control much faster. So there we basically know nothing except some examples of interesting behavior. So here we are on a level when we collect already general theory statements, and there we are still on a level when we build examples. So it's not very... Yes.
How do I understand this? So is it correct that the lengths are something like distances between saddle points on the...
More or less, you can think about them just as integrals of your one form over a basis in homologies. And so since you lived in T3, you have very little number of members of this set. You have only 3 independent integrals. Despite the fact that your surface has a high genus, so it's supposed to have like 6 independent integrals, it has only 3. So that's you can see them as results of integrating of your one form, this length.
Why these integration cycles are homologous cycles of surface, but not distances between the saddle points?
It doesn't matter what. I mean, it depends how do you choose a transversal in some sense. Of course, what are precisely your lengths. But it does not matter. It just, you can measure whatever distance, just your dimension of this set is small because you have only this number of independent bases. So when you start to express also the distances, you will necessarily be limited in this. Danton.
They are the fact of the family of forms in this room before linear form of T3 and three dimensional vector space.
They are too restricted living in T3, that's what I want.
Can you explain about this theorem? Can equal to 3 and 4? Is it an artifact of the family that can prove it only for 3 and 4, or is it something really specific for surface genus?
Well, we don't know exactly because they can prove it. Their proof is extremely technical, as I told you, and it works. They proof works. They apply some kind of induction and they analyze what happened to the Rosy graph. But the graph is enormous, of course, because if you consider a standard plan, you are kicked off from the class of fully flipped. You need to understand.
I can reformulate my question. Do you explain that this would be true for energy?
We are not, no, because we definitely do not have a connection between Novikov's problem and this thing starting from n equal to 5. So I don't see, my intuition does not tell me anything in this case. And at the same time, their proof is not extendable at the current level of computer ability.
And it wouldn't help you for Novikov's problem?
No, because here you exploitate the fact that you have an involution. Mm-hmm. And if you consider non-symmetric surface in Novikov's problem, that's what we are supposed to do if we increase the number of parameters. You will not have such an involution on the surface anymore that you used to factorize.
Why can't you consider surface of genus 4 which is symmetric, or 5?
No, maybe this you can. What I mean is that what we cannot is to go higher in the sense of generality in genus 3. You consider non-symmetric surface, like such a picture.
No, I was speaking about hygiene.
With higher genus, I don't know, I'm not sure it's related, so I don't know. In genus 3, you lose it, so it will not give you proof for a general Novikov conjecture for sure. If it works only for this.